All right, good afternoon, everyone. Thank you for joining us for our advanced Skywarn training. We do this every couple years. We do basic trainings a little bit more regularly. The main difference between this training and the advanced training, or between the basic training and this training, is in the basic training, we basically tell you what to report and what stuff looks like, whereas in this training, we dive into the science a little bit more. So we will still show you some pictures of clouds and tornadoes that you might see around here and that you might be calling in to report to us. But you'll also learn hopefully a little bit of science behind what drives thunderstorms and severe weather around here. So, a quick summary of our office here at the National Weather Service in Cleveland. When we're fully staffed, there's about 25 of us, a few less at the moment, but that staff is spread between forecasters, support personnel, management, people who help with our observing program, hydrology, that's like river flooding and stuff like that. And all of us are here 24/7 to keep weather watch on the local area. And we have the responsibility of issuing all watches, warnings, and advisories for the area, including tornado, severe thunderstorm, and flash flood warnings. And that is certainly of key interest for this presentation, for this severe weather training talk. So we are one of 122 weather forecast offices across the country. So our next closest ones are Pittsburgh, Wilmington, Ohio, Buffalo, and Detroit. And there's a look at our operations area. We have 9 workstations in there, and during a bigger severe weather event, we'll fill all 9 of them. But normally there's 2 or 3 of us here at any given time, working on the forecast and watching the weather. And this is our area of responsibility. We cover 30 counties across Ohio and northwestern Pennsylvania, with about 5.5 million people living in those counties. So quite a few people that we are responsible for providing forecasts and warnings for across the 30 county area. So here are a few more stats about our forecast area. On top of the 30 counties we cover on land, we have what are called marine forecast zones. Those are basically the size of a county over Lake Erie. We also have river forecast points that we produce forecasts and warnings for. 7 airports across the area, including Cleveland Hopkins, that we have to produce forecasts for. Several climate stations across the area. Along with weather radio broadcasters, we have 10 weather radio broadcasters across the area. We have a couple radars, and our forecasts cover parts of 5 media markets. So again, a nice chunk of area that we have to keep an eye on for forecasts and warnings, and we also have to maintain weather observing equipment and stuff like that across the area. So it can keep us busy, that's for sure. So again, what do? We're here 24/7 providing that weather watch, as we call it, issuing forecast watches and warnings. We also work quite a bit with local government. So, say, for example, the city of Cleveland, we work with a lot of emergency management offices. Every county has an emergency management office, just to make sure they're getting the best weather information and have the best safety plans in place for the public in case bad weather is heading towards their county. So along with those forecasts and warnings, which really is like the most important thing we do, maintaining those relationships is a very close second, because again, we want to make sure people are getting our information and are understanding it and are providing us feedback when things go poorly or when they go well. So we're both on the internet and on social media. Our web address is weather.gov/CLE. We also have a Facebook page, an X account, formerly Twitter. We're also on Instagram and YouTube, although I would say Facebook and X are where we post most often on social media, and then our website always has the most up-to-date information. So kind of moving beyond the quick introduction about our office into the kind of meat of the presentation, starting off with a look at thunderstorm ingredients. What atmospheric phenomenon do we need to generate severe thunderstorms or severe thunderstorms in particular? So basically, we need instability. Instability means rising air is warmer and more unstable than the air around it. And that happens when it's really warm near the ground, a little colder aloft. We also need some amount of moisture. Obviously, thunderstorms are full of clouds and rain, so you need moisture. Also some lift, and then severe thunderstorms also require wind shear. So we'll delve into all these ingredients a little bit more. So first off, starting with instability, hot air rises, and that's really the beginning of a thunderstorm, is getting warm or hot air that is rising up through the atmosphere. And that most basically starts developing when the sun's out and it starts heating the ground up. And that is why the afternoon and evening hours are when we most commonly see thunderstorms around here. We can get thunderstorms at night, but it becomes a little bit harder the later in the night you get. So once the ground is warm, the larger the temperature difference between the ground and the air a little bit above it in the atmosphere, that gives you more instability. So warmer ground, colder air above it means more instability, because that'll make the hot air near the ground really want to rise. So instability is maximized when it's warm and sunny with cold air aloft. So, take today, for example, we do have that little risk of severe weather, and we do have a line of kind of gusty thunder showers moving across Northeast Ohio right now. Today, we were kind of lacking the warm sun. It was kind of cloudy and rainy all day, but it is a little bit chilly aloft today, so there's a little bit of instability. So basically, the most simple way we measure instability is what we call the change in temperature with height, or the lapse rate is the more technical definition. And lapse rate, it's literally just how quickly does the temperature change over a certain distance and height through the atmosphere, or as you go up through the atmosphere. So we need this lapse rate to be at least 6 degrees Celsius, that's about 10.5 degrees Fahrenheit per kilometer or higher, for there to be what we call instability in the atmosphere. The higher that number is, the more instability there is. So where moisture comes into play is if you have air rising and it's saturated, it's forming a cloud, it will cool slower as it goes up compared to dry air rising. And the reason is when a cloud forms, it condenses and it gives off latent heat, which that doesn't happen when you just have dry air that's lifting up. So humid air near the ground tends to lead to more instability. So that's why a 90-degree day with a really high dew point, it's really humid and miserable outside, that tends to be when we get more of our summertime thunderstorms, as opposed to a day where maybe it's 90 degrees but not so humid, which is pretty uncommon around here. So basically, as the last bullet point says, if we have instability, it supports air that's moving up faster and faster until it hits the tropopause, that's the top of the troposphere, usually 40 to 50,000 feet above our heads. So an unstable environment that promotes that rising air is most favorable for thunderstorms. You need that rising air for thunderstorms. So this is, again, really getting into the weeds, but we talked a little bit about the sun heating up the ground being important and the cold air above it being important. One way we can get, especially unstable air, is when we have the development of what's called an elevated mixed layer. And you can sort of make out the arrows on this map. So basically what the elevated mixed layer is we get a layer of very unstable air that develops aloft over the Rocky Mountains. And then it can actually blow east across the country. It's not extremely common for this unstable air that develops all the way over the Rockies to make it all the way to Ohio or Pennsylvania without kind of losing its potency, but a few times a year it can. And when that happens, that is when we tend to get our biggest severe weather outbreaks around here. So a famous example of an elevated mixed layer is May 31st, 1985. We're actually coming up on the 40-year anniversary of what was a very potent tornado outbreak from Northeast Ohio into Pennsylvania and New York. There was an F5 tornado that touched down in the Newton Falls area and then tracked through like Niles and Ohio and into Wheaton, Pennsylvania with that outbreak. That had an EML. So our most prolific severe weather days happen when we get this elevated mixed layer that comes and blows east from the Rockies, while at the same time you have moist air kind of represented by the green arrows moving north out of the Gulf of Mexico. That combination is our most prolific severe weather producer around here. We get it maybe a few times per year. They get it much more often out in the plain. So another way to measure instability, and I would say this is the most common way we look at it here, kind of behind the scenes when we're putting together a forecast, is what's called CAPE, and that stands for Convective Available Potential Energy. So here's a little table kind of giving some representative values. So this is a calculated field. It's basically area under the curve. If any of you took some advanced calculus classes or differential equation classes in high school and college, basically CAPE is area under the curve between the temperature of a rising air parcel and the environmental temperature. So when you get rising air that's warmer than its surrounding environment, you get instability, and when you add that up through the whole atmosphere, you get an amount of CAPE. So CAPE, it's easy to calculate for us, and there is a relationship developed between the amount of CAPE and how fast the air is actually moving up through a thunderstorm. So thunderstorms, they have what's called an updraft, and we'll talk about that on one of the next couple of slides. And that updraft transports this warm air through the thunderstorm, and it's really the fuel of the thunderstorm. And these updrafts can be blowing straight up at over 100 miles an hour in severe thunderstorms. And you need those higher CAPE values, generally over 1,000, to get those updrafts that are strong enough to produce severe weather. A good rule of thumb is if you have hail that's a golf ball sized or larger, at least the size of a golf ball, you need an updraft that's blowing straight up through the thunderstorm at over 100 miles an hour to get hail that big. Otherwise, it falls out before it can get that large. So delving a little bit more into moisture. So as mentioned earlier, moisture directly influences the amount of instability or CAPE. Because when you have moist air that's rising, it's going to form clouds, which give off heat, which increases the amount of instability in that column of air that's rising through the atmosphere. So a very common method or common parameter we look at to measure moisture is what we call precipitable water, which is literally just you take the entire atmosphere or column, as we call it, and add up all the water that's in it and come up with this value of how much water is in the entire atmosphere. Usually around here when we're getting thunderstorms, the precipitable water value is 1 to 2 inches. Once you get over 2 inches, that's really quite high for Ohio and Pennsylvania, and that's when we really start worrying about flash flooding potential. Aside from precipitable water, a more common, at least in terms of, you'll see these numbers on the TV or on the internet, is dew point. That is also a measure of moisture. And dew points are measured at the ground, whereas precipitable water is a more kind of all-inclusive number. So there could be rare occasions where the dew point is pretty high near the ground, but it's very dry aloft. And vice versa. Sometimes maybe if you're north of a warm front, the dew point's lower, but it's still pretty humid aloft. So sometimes precipitable water and dew point can be a little bit out of phase, but they're both ultimately measurements of moisture. And you can see that little bar there on the right. So today our dew points are right around 60 degrees, and you see there we tend to consider a 60-degree dew point to kind of be the minimum for what we look for strong to severe storms. So we're kind of right on that cusp today, and it's why we have this real kind of marginal, debatable severe threat today from eastern Ohio into Pennsylvania, and it's really just over the next few hours before it moves east out of the area. So a note about relative humidity, you can kind of see that in the last bullet point, and then in that picture there on the bottom left. Relative humidity is, as the name says, relative, and what and the reason that's the case, or why that's an important distinction, is it's because warm air holds more water. So for a 100% humidity with a temperature of 95 degrees, you would need a dew point of 95 degrees. But as that chart shows you there, a 50% relative humidity at 95 degrees is a dew point of only 74, which is quite a bit more moisture than a 50% relative humidity, even at 75 degrees. So that's why we often look at precipitable water or dew point more so than relative humidity to get a true sense of how much moisture is present in the atmosphere, just because relative humidity can be a little bit misleading because you can get high RH values when it's cold, but with low dew points. You can also get relatively low RH values when it's very hot and with fairly high dew points. So moving on from moisture and instability to lift. Lift is basically anything that makes air in the atmosphere want to start going up, and lift is needed to start creating clouds and thunderstorms. Really, how the process works is you get lift that gets the atmosphere moving, and then if the atmosphere is unstable, it'll keep moving upwards until you have a thunderstorm. So you need lift and then you need instability. That's kind of the order for a thunderstorm. So what can force air to start wanting to move up in the atmosphere? Fronts are a big one, especially cold fronts. Warm fronts a pretty big one too. Mountains, not so important around here. Lake breezes can be quite important. Lake breezes kick off a lot of thunderstorms in the summertime around here near the Lake Erie shoreline. Old storms can, get the atmosphere moving as well. So here's a schematic of a cold front pushing into a warmer air mass from left to right. And you can see the front itself, it's, a very sharp gradient or boundary with different wind directions and temperatures on either side of it. Warm air is always less dense than cold air. So when you get cold air kind of pushing in with the cold front, it wants to lift the warm air in front of it. And that lifting motion can get thunderstorms to develop along a cold front, assuming it's unstable enough. Warm front, similar process, although that's a little bit different because the warm air is kind of getting lifted up over a receding cold air mass. But either way, you can still get lifting air with a warm front. So, along and just ahead of warm fronts can be a spot for thunderstorms to develop as well. Again, mountains, we don't really have mountains around here. We have hills. But if we were to have bigger mountains, that is definitely something, especially out west and even in the Appalachians, where you can get storms developing on top of mountains, just because the air must rise to go over the mountain. The wind is not going to go through the mountain. So around here, this is a elevation relief map of our forecast area across northern Ohio, northwestern Pennsylvania. This ranges from a little bit under 600 feet along the Lake Erie shoreline to up to 15 or so hundred feet near Mansfield, and then up to about 1,800 feet in extreme eastern Erie and Crawford counties in Pennsylvania. So we have a little over 1,000 feet of elevation change across our entire forecast area, which can be just enough. Sometimes we'll see storms intensify as they move maybe out of northwest Ohio and into those hills. But it's not a huge factor for us around here. So here is an example on a weather map of thunderstorm initiation. So this weather map, we have a cold front that is the blue line with triangles coming off it, kind of stretching from southern Minnesota across Iowa and into Kansas. And then right ahead of the cold front circled there, we have what's called a prefrontal trough, which is just, kind of a weaker boundary just ahead of the cold front. Very common for cold fronts and warm fronts, as I said, to kick off thunderstorms. Prefrontal troughs are also something we always have to watch for, especially when you get into the summer months and it's very warm and humid and unstable. Any source of lift, including a prefrontal trough, is something that might kick off thunderstorms. So kind of here is that example on satellite playing out. You can kind of see early in the loop, we'll catch it. There's nothing, and then right along that frontal boundary on the prior image, a big cluster of thunderstorm develops kind of right in there, and it goes kind of, once the air lifts, it's very unstable and it keeps going. So now that's very often how things play out in the spring and summer around here when we get thunderstorms. We, maybe have a warm, humid air mass in place. Maybe we've been heating up through the afternoon, ideally, and then late afternoon, early evening, a front comes in, adds lift, causes thunderstorms to develop, and then they develop and keep going until they run out of instability. So, instability, lift, moisture, those are all things we need to get thunderstorms to develop. Wind shear is the big ingredient for getting thunderstorms to become more organized and turn severe. And so what is wind shear? Wind shear is just a change in wind speed or direction, sometimes both, as you go up through the atmosphere. So there are two types of wind shear. There's directional shear, that's the change in wind direction as you go up through the atmosphere. And then there's speed shear, which is when the wind increases in speed as you go up through the atmosphere. So some combination of one or both of these is usually needed to get organized severe thunderstorms around here. So here is kind of in pictures, and these are real life pictures, of course, two examples. One is a very low wind shear example on the left, where the thunderstorm develops, it goes straight up, and then there's no wind shear. So the thunderstorm just kind of sits there. And then the thunderstorm, it literally just rains itself out. The chilly, rainy air falling out of the thunderstorm cuts off the warm, humid air getting lifted into the thunderstorm, so the thunderstorm develops, rains itself out, and then it's done. And this can happen in less than an hour, and it's uncommon, not impossible, but uncommon for these little kind of popcorn thunderstorms like you see on the left to turn severe. And then on the right, you have a kind of a very distant picture of what is a supercell thunderstorm. And you can kind of tell how the warm, humid air is getting drawn into the thunderstorm from the left. You can kind of see that line of clouds literally feeding into the thunderstorm. And then you see the rain falling on the right. And that's what wind shear does. It keeps the warm, humid air that's fueling the thunderstorm separated from the rain-cooled air falling out of the thunderstorm. So when you have wind shear, that's when storms tend to last longer, gives them a greater opportunity to turn severe, gives them a greater opportunity to rotate and maybe produce some tornadoes. Squall lines in particular, wind shear in the lowest levels, the lowest 3 kilometers, that's about the lowest 9 to 10,000 feet, is very important for the persistence of squall lines, because squall lines develop usually, along something like a front, or maybe as thunderstorms, maybe they develop and turn into a cluster and organize into a line. If there is not enough wind shear in the lower levels of the atmosphere, as you can see on top, the cold air kind of behind the front, maybe it's a cold front, maybe it's just the gust front from the thunderstorms. The colder air will want to rush out ahead because of how dense it is and low to the ground it is. It'll want to rush out ahead of the thunderstorms, and it'll want to cut off the air fueling into the thunderstorms if there's no shear. But if you have a squall line and you have a lot of shear in place, the cold air and the thunderstorms are much more balanced. So the cold air will kind of be behind the leading edge of the thunderstorms. It'll stay there, and the thunderstorms along the leading edge of the squall line will remain very robust and vertical. They're not getting cut off. So squall lines, usually when we have organized long-lasting squall lines across our forecast area, or really anywhere, there is a fair amount of shear in place, and the lowest about 10,000 feet of the atmosphere. So beyond, so this is just kind of talking about speed shear in the lowest few kilometers. It's quite important to squall lines. But something that's very important to rotating thunderstorms and tornado potential is something that we call storm relative helicity. And there will not be a quiz on these terms at the end. But what helicity is it basically quantifies the change in wind shear over the lowest, whatever level of the atmosphere you want to look at. This chart here is highlighting the lowest 3 kilometers. But basically, you can kind of picture this on the right. This chart traces out the wind speed and direction as you go up through the atmosphere. So you can kind of picture how the wind speed is increasing as it moves away from the middle of the graph. The middle of the graph is 0 wind. So as you move away from it, the speed is increasing. You can also get an idea that the wind is turning or changing direction with height. That's why the line kind of moves away from the center and then it starts curving to the right. This low-level turning is very important to rotating thunderstorm potential and tornado potential. So, when we're trying to forecast severe weather and then when we're trying to issue warnings for severe weather, we're looking at both how much the wind increases as you go up through the atmosphere and if the wind changes direction in the low levels of the atmosphere. So there's a couple of situations where we might have a lot of this low-level wind shear. One is near a warm front. And then the other one that is most common around here is along and ahead of a cold front when you have a strong low pressure moving into the region. Strong low pressures and warm fronts both can really increase low-level wind shear, both speed shear and directional shear. So, both cape and wind shear or instability are important to severe weather potential. The more instability or cape you have, the greater the severe weather potential you have, because the storms themselves will be, they'll develop quicker, they'll have stronger updrafts, and then wind shear allows the storms to persist and organize. So this chart on the right is a very rough relationship between instability or cape on the left and then wind shear on top. So I'll tell you what these words on the chart mean. When we say ordinary, we mean kind of just popcorn thunderstorms. They develop, they rain themselves out, they don't last very long. Multicells, that is what we would, a cluster of thunderstorms or a line of thunderstorms, we would consider that multicells. So more organized than the ordinary cells. And then supercells in red, that is the most organized or intense type of thunderstorm. A supercell is a rotating thunderstorm. It's on its own. Supercells have the greatest risk for severe weather. So in general, more shear and more cape favor more intense and more organized storms. One note is that in the cold season, we can get severe weather with less than 1,000 joules per kilogram. Pardon me, that's the unit for cape there, J over kg, that's joules per kilogram. We can get severe weather in the cold season with less than 1,000 joules a cape, just because there is so much lift in the atmosphere in the cold season and usually so much wind shear. It doesn't take much cape to get severe weather in the winter. And then, just again to compare today to this chart, today we have less than 1,000 joules per kilogram of cape, but we do have about 50 knots of 0 to 6 kilometer shear. So that kind of puts us in the range there in the upper right, where we can get multicells or supercells. And so far today, things have been it's been more of a line of showers and thunder showers moving across the area. Yeah, the big limiting factor today to more widespread severe weather is the instability being kind of limited. I see a chat in here from a few minutes ago. Is the slide deck stuck, or are we? If someone can type in there real quick, are we looking at assessing thunderstorm ingredients with a skew T? Is that the slide you guys are seeing? Okay, I'm seeing a bunch of yeses. Thank you. All right, so assessing thunderstorm ingredients with a skew T. I'm not sure if someone is still stuck on the CAPE table. I'm not sure why. Maybe just refresh your browser, see if that fixes it. So in terms of assessing thunderstorm ingredients with a skew T, if the slides get stuck for more people, let me know. For most people, it looks like it updated. So what is a skew T? We'll label some lines here. So a skew T is a vertical plot of temperature, dew point, and wind. And it's something that allows us, when we're assessing severe weather potential, to kind of look at all the things we were just talking about in one plot. So on this chart, the red line is the temperature as you go up through the atmosphere. So you have the surface here at the bottom of the plot, all the way up to, that's about 70,000 feet at the top of the plot. So a very deep layer of the atmosphere. The green line is the dew point. So the closer the temperature and dew point lines are together, the more humid the atmosphere is. On the right, we have winds as you go up through the atmosphere. So in this case, there is not a whole lot of wind as you go up through the atmosphere, but you can see there are barbs. So one line, one full line is 10 miles per hour or 10 knots of wind. Knots, it's 1 nautical mile per hour. The short line, that's 5 miles an hour, and then the flag is 50. So on this plot, there isn't a whole lot of wind as you go up through the atmosphere. And then this dashed line, so when I was talking earlier about how rising air can be warmer than the air around it, especially if it's humid, that's what this line represents. So when you kind of take the difference between the red temperature line, or the area between the red temperature line and this gray dashed line, the area between those two is CAPE, or instability. So on this plot, we have a lot of CAPE over 2000, but only about 20 knots or miles an hour of shear in the lowest about 20,000 feet of the atmosphere. So this would be a sounding that probably supports just ordinary thunderstorms. And these soundings are available on the internet. We do have a few offices around us that launch air balloons that take these soundings as they go up through the atmosphere. And you can view them on the internet at the web address there below. So just to kind of sum up all the thunderstorm ingredients, someone, not myself, came up with the acronym SLIM to sort of remember all these thunderstorm ingredients: shear, lift, instability, and moisture. And the main message for severe weather is the more of these you have in place, the more favorable the atmosphere is for severe weather. You can still get thunderstorms if one or two of these ingredients are lacking, but organized severe weather, you usually need some combination of moisture, instability, lift, and wind shear, with wind shear being the most important for more severe thunderstorms. So kind of moving beyond some basic thunderstorm ingredients and some of the things we look at behind the scenes when we're trying to put these forecasts together for severe weather, into kind of how thunderstorms work. And I used some of these words a little bit earlier on. So updraft, I'm missing an R there, updraft, not updraft. So the updraft is the part of the thunderstorm where warm, humid air is getting lifted through the thunderstorm. It's all these red arrows here inside of this red circle, that represents the updraft in this thunderstorm. Without an updraft, you don't have a thunderstorm. So one way that you may be able to see the updraft if you're ever out in out and about looking at a thunderstorm coming in is, you can usually tell where the rain is dumping out of the thunderstorm. But if you kind of find the area adjacent to where you can see the rain falling out of it, you'll usually see a well-defined cloud base where there is not rain falling out of it. That's usually where the updraft is, because you have the updraft moving upwards and preventing the rain from falling out of the thunderstorm where the updraft is. But that updraft is still moving up and causing the clouds to form. So, if you ever see a thunderstorm coming in, if you can ever kind of spot, usually it's near the edge of the rain where you have some very dark, ominous looking clouds, but rain isn't coming out of it, that's usually where the updraft is. And a lot of times if you're going to get something like a tornado, it'll develop near the edge of the updraft. And then you have the updraft and then downdraft. So didn't miss an R here, downdraft. That is just where the rain-cooled air is falling out and rushing out of the thunderstorm. So usually you need an updraft to last at least 10 minutes to start getting a shower or thunderstorm to form. Once that happens, you get what we call hydrometeors. So that's either ice crystals or liquid drops, or both, depending on how high up you are in the thunderstorm. Those begin to form and then they start falling out. As the hydrometeors, as we call them, start falling towards the surface, they bring colder air from aloft with them and start developing a downdraft. So something that we look for here when we're trying to assess severe weather potential is actually dry air in the mid-levels of the atmosphere, and I'll briefly explain why. When there is dry air aloft, once you get maybe 15 or 20,000 feet aloft in a thunderstorm, that dry air, if it gets blown into the thunderstorm, it'll actually want to cause the thunderstorm to start evaporating. And evaporation is actually a cooling process. Energy is transferred from the air to the hydrometeors that are evaporating, and that can actually help develop a cold pocket of air in the mid-levels of a thunderstorm that begins descending towards the ground as a downdraft. So, especially for, if damaging winds are our main severe weather hazard, we'll actually look for a punch of drier air in the mid-levels of the atmosphere to help increase that threat. A shelf cloud is a very common but not necessarily ominous or severe cloud that you can sometimes get on the edge of a downdraft where that rain cooled air is starting to rush out of a thunderstorm. So shelf clouds form when rain cooled air starts rushing out ahead of a thunderstorm. It sort of starts acting like a mini cold front, and the rain cooled air starts lifting up the warm air in front of the thunderstorm. And as that warm air starts getting lifted into the thunderstorm, it starts forming the shelf cloud on the leading edge of the thunderstorm. So shelf clouds, the big giveaway that you're looking at a shelf cloud and not something that might be more tornadic is it'll be a horizontal feature. So it'll be attached to the thunderstorm. It'll be horizontal. There will not be vertical rotation with it. There might be some turbulent motion, but you're not going to see rotation with a shelf cloud. So shelf clouds are something that can be mistaken for something more tornadic, especially if you see it maybe in the distance or maybe from the side. But the big giveaway is it's kind of going to be associated with you'll usually see the rain cooled air right behind the shelf cloud. You'll see the rain, and the shelf cloud itself will not be rotating, even if it's a little bit lower to the ground. So, shelf clouds can really occur with any type of thunderstorm, although they're most common with squall lines and supercells. But speaking of the different types of thunderstorms, we touched on these a little bit earlier, but we kind of classify thunderstorms based on how organized they are into different groups. An ordinary thunderstorm or a single cell thunderstorm, or more commonly known as a pulse thunderstorm or a popcorn thunderstorm. These are very common mid to late summer on days where there is not much wind shear, but it's still very hot and humid, so you have instability. Ordinary thunderstorms, it is just a single cell that develops. You can kind of see that stage on the left. Once it develops long enough and rain starts falling out of it, we call it mature. And before long, these single cell thunderstorms just rain themselves out. The rain cooled air rushing out of the thunderstorm cuts off the updraft and the thunderstorm rains itself out. So single cell thunderstorms have the lowest risk for severe weather associated with them. You can get, a quick wind gust, maybe a little bit of hail if you have a stronger ordinary thunderstorm, but you're usually not getting tornadoes or widespread severe weather or large hail with these single cell thunderstorms, just because of how brief they last. So once you kind of move up from single cell thunderstorms, you have what we call multi-cell thunderstorms, and you start getting this increased level of organization with a little bit more wind shear in the atmosphere. So multi-cell thunderstorms, the rain cooled air is just a little bit more separated from the updrafts feeding into the cluster of thunderstorms, and that allows the whole system to just become a little bit larger, last longer. It's a little bit more organized. I would say, in terms of thunderstorm features you may see with an ordinary single cell thunderstorm, you'll probably see a rain-free base with the updraft until it starts raining itself out, and you might very, very briefly see a shelf cloud. But otherwise, ordinary cell storms, you're not going to see much. With multi-cell storms, you'll certainly see a rain-free base under those new towering cumulus or new thunderstorms developing on the edge of a multi-cell cluster. And with multi-cell clusters, shelf clouds are a little bit more common because once you get storms organizing into clusters, they develop a nice little pool of colder air. It's called a cold pool, so a good name for it. And on the edge of that cold pool, you usually can get a little bit of a shelf cloud. And once multi-cell thunderstorms are especially organized, they can form into more intense squall lines or even derechos. So usually these more organized multi-cell thunderstorms, they happen when the wind shear is even stronger, and or if there is a stronger lifting mechanism in the atmosphere. So maybe a frontal boundary, maybe some lift associated with systems moving through the jet stream. That's usually when we get these more organized derechos or squall lines. In a derecho, I believe I have the definition on one of the upcoming slides, but a derecho is just an especially intense thunderstorm wind event that lasts longer than normal. So it's a long-lasting, intense thunderstorm wind event. So here is an example of a derecho, and I would say this is the last time a classic derecho affected our forecast area. This was from August of 2023. Early in the loop, thunderstorms start developing over Wisconsin and Michigan. Over time, they organize into a cluster and begin accelerating. They blast right across northern Ohio and into western Pennsylvania. And these thunderstorms were severe all the way through the Charleston, West Virginia area. So you see the definition of a derecho there on the right. It needs to track at least 240 miles with wind gusts to severe levels, so that's 58 miles an hour or higher along pretty much the entire length of the path, with some wind gusts over 75 miles an hour in there. So it is a pretty robust definition. I would say we, on average, see one every year, give or take, in our forecast area. So here's the damage that radar loop produced. These are storm reports that the Storm Prediction Center collected. All the blue W's are wind damage reports. Any green H's are large hail reports. Any red T's are tornado reports. So this squall line was a little bit low end in terms of distance for a derecho, but for those of you who might remember, this did quite a bit of damage across northern Ohio. We had 12 tornadoes across our forecast area with the squall line. We also had quite a bit of straight line wind that in some cases we estimated to be 80 or 90 miles an hour. So I guess going back real quick to thunderstorm features you might see with a squall line or derecho, shelf clouds are a big one with squall lines and derechos. They almost always have a really big shelf cloud on the leading edge of them. And very intense squall lines and derechos can produce tornadoes. Most intense tornadoes come from what we call supercells, which is on the next couple of slides, but very intense squall lines can produce short-lived tornadoes. So here's another example of a very intense squall line from last summer. Those in the Cleveland area are certainly going to remember this case because this produced First Energy's biggest power outage by number on record, by number of customers knocked out. And some of those outages lasted about a week. So this was a cluster of thunderstorms that developed over Lake Erie in Northwest Ohio, very quickly blasted through our forecast area, and then it fell apart by the time it got past Pittsburgh. So that is why this one was not quite technically a derecho. We were just a little bit short on the length, but otherwise it hit all the other criteria. So just because you have a really nasty squall line doesn't necessarily mean you have a derecho. And this is why you usually, if you pay close attention, we're usually not predicting a derecho ahead of time. Instead, we're predicting the risk for damaging winds, the risk for tornadoes, the risk for large hail, just because a derecho is a very strict technical definition, and you can get an event like this that's not quite a derecho that is just as bad as some derechos are if it hits you just right. So yeah, this event produced quite a bit of straight line wind damage. We estimated up to 100-mile-an-hour winds in the eastern Cleveland suburbs with this case. It also produced 5 tornadoes in our forecast area, a little bit of hail, a little bit of flash flooding as well, and that was last August. And so moving on to the most kind of dangerous type of thunderstorm, and probably the least common around here in northern Ohio and northwestern Pennsylvania, supercell thunderstorms. So what do you need for supercells? You need strong instability, and you also need strong wind shear, because supercell thunderstorms have a rotating updraft. So you need strong wind shear to kind of give you that spin in the atmosphere. If you remember back to the wind shear slide, strong wind shear actually creates kind of a rolling motion in the low levels of the atmosphere, which a strong thunderstorm like a supercell can actually pull in and acquire rotation from that. So most supercells, or most of our storms around here aren't supercells, but we do see them maybe a few times a year. Most supercells produce severe weather in terms of damaging winds and large hail. And supercells produce the vast majority of very large hail. So hail that's 2 inches in diameter or larger almost exclusively comes from supercells. Only about 20% of supercells produce tornadoes though. So supercells are kind of the thunderstorm type where you might see all sorts of different cloud formations that as a spotter might get your attention. So obviously the biggest, I don't know if attraction is the right word for a supercell, but the most ominous cloud you might see from a supercell would be a wall cloud with a tornado underneath it. So I mentioned earlier, if you can kind of find the rain-free base where the updraft is in a thunderstorm, oftentimes right along the edge of that rain-free base and where the rain is falling out of the thunderstorm is where a tornado will develop if you have a supercell. And you can kind of see that on the schematic. So what is a wall cloud? A wall cloud is a very distinct, persistent, well-defined lowering beneath a thunderstorm updraft. I see it's getting a little wet there in Erie. Hopefully nothing severe there. I'm just reading a couple of comments that came in. So a wall cloud is a very distinct, well-defined lowering. It's going to be persistent. It's usually going to be on the edge of the rain. The supercell in this schematic would be moving right to left, or left to right, pardon me. So from the left side of the screen to the right side of the screen is where the supercell would be moving. So this is what it would look like sort of out in front of, maybe to the south of the supercell if you're looking north at it. So usually if there's a tornado, it's going to be underneath that wall cloud. And sometimes with a supercell, you can get a shelf cloud, especially on the leading edge of where the rain and hail is falling out of the thunderstorm. So supercells can produce all severe weather hazards, including the largest hail and the most intense and long-lived tornadoes. And again, fortunately, we see true classic supercells around here maybe a few times a year. So a little bit more information about supercells. Supercells can have very often updrafts with winds blowing up through the thunderstorm at over 100 miles an hour. The downdrafts associated with supercells can produce very strong damaging winds. Supercells also produce a majority of our very large hail. So, you know, this is kind of if you're looking at a supercell from the ground on this slide, this would be if you're looking at a supercell from above, and this might kind of be what a supercell would look like, at least a classic supercell on radar, if you see the color fill there, the greens and oranges and reds. So, you know, the schematic of a supercell is the updraft is in the middle of the thunderstorm where the warm, humid air is getting drawn into it. And then you kind of have an expansive area of rain-cooled air, both in what we call the forward flank downdraft. That's where rain-cooled air rushes out ahead of the leading edge or the forward flank of the supercell. And then we have what's called a rear flank downdraft, where rain-cooled air gets wrapped around the backside of a supercell. And you can get damaging winds and shelf clouds along the leading edge of both downdrafts. And usually if you have a tornado, it's going to kind of develop right on the edge of the updraft and the downdraft area. So, you know, here's kind of a couple more schematics here. Shelf clouds are most common if you're on the forward flank of a supercell. You can sometimes get them on the rear flank as well. The tornado is kind of going to be in the middle, and oftentimes you'll get a flanking line of clouds along the rear flank downdraft, and sometimes that flanking line of clouds will get drawn into the updraft and sort of help the whole process along. So a couple different types of supercell thunderstorms. You know, like anything, supercells can come in all shapes and sizes. The main commonality is all supercells have a rotating updraft, but some of them produce a lot more precipitation than others. This is very dependent on how humid the atmosphere is. So a low precipitation supercell might be something that develops more commonly out in the plains where the atmosphere just is not as humid. And then a high precipitation supercell, that's much more common around here if we do get supercells. You can sort of tell from these schematics that high precipitation supercells, they're usually larger, and sometimes the rain makes it a little bit harder to see some of the structure underneath them. And high precipitation supercells are a little bit more common around here. So we always encourage folks to be very careful if you're, you know, out and about and you're trying to see thunderstorms. We do not encourage people to go out and chase just to give us reports. And the main reason is because we have a lot of trees around here, especially once you get farther east in Ohio and into Pennsylvania. A lot of trees, we have some hills, and a lot of times we have some very high precipitation storms that just make it a little bit harder to see the dangerous parts of them. So, you know, that's why we love any spotter reports we get. They're very important to us, but we do not want people putting themselves in harm's way to get storm reports for us. You know, if you see a storm moving through your area that's doing damage, or maybe has some interesting cloud features with it, such as a wall cloud or a funnel cloud or a tornado or even a shelf cloud, we certainly want your information. It's very helpful for us when we're issuing severe thunderstorm and tornado warnings, but it's not, you know, something that we want you putting yourself in harm's way to call us for. So, you know, this kind of sums it all up, kind of the different parts of a supercell, where you may see different cloud features. So, and I kind of like that it puts both the top-down view and the view you might see if you're on the ground into one slide. So you kind of see the person icon. That is kind of the view if you were looking at the supercell on the ground, is where the person icon is there on the left-hand image, sort of ahead of and to the south of the supercell. So again, tornadoes usually form kind of where the inflow and the outflow meet. Supercells in particular are storms that sometimes they can split into two, especially earlier in their life cycle. They can turn, you know, they can be moving one way and it can look like they're taking a right-hand turn if you're looking at them from above on radar. Storms can merge, they can quickly develop and dissipate. And they can produce lightning, you know, well outside of where rain is occurring. So again, safety first. If you're out and about and spotting or looking at thunderstorms, you know, when thunder roars, we say go indoors. And if a severe thunderstorm or tornado warning is issued for your area, we encourage you to take cover in a safe location and not to necessarily go out and look for these cloud features. So diving into what thunderstorms can produce, and you know, the most common one is lightning, and lightning is not what makes a thunderstorm severe. Every thunderstorm contains lightning by definition. You cannot get thunder without lightning. Lightning generally transfers negatively charged energy or negative electrical charge from the bottom half of the thunderstorm towards the ground. But every once in a while, you can get positively charged lightning strikes that come out from the top of the thunderstorm and make their way all the way to the ground. When that happens, they're usually much more prolific. So how lightning forms, how you get these different charges in different areas of the thunderstorm cloud compared to the ground is normally closer to the bottom of the thunderstorm, you have rain or you have liquid drops getting lifted up through the thunderstorm, but the thunderstorms extend well above the freezing level, and there's usually a good portion of the thunderstorm where both liquid drops and ice crystals or even hail are coexisting. And where that happens, the liquid drops rub up against the ice crystals and actually create static electricity in the thunderstorm. So that is why you need these clouds to get tall enough to produce thunder and lightning, because you need that, you need part of the cloud to be frozen, part of the cloud to be liquid, and you need those two parts of the cloud to interact long enough to start getting these electrical discharges outside of a thunderstorm. One way to tell a positively charged lightning strike from a negatively charged lightning strike is by the sound of the thunder. Positively charged lightning strikes, those are the ones that produce the loud rolling rumbles of thunder that shake the whole house. Those are positively charged lightning strikes. And then your more standard, quick crack of thunder followed by more of a distant rumble, that's usually a negatively charged lightning strike. So in terms of what makes a thunderstorm severe, lightning does not make a thunderstorm severe, although it is certainly a hazard with thunderstorms. Flooding does not make a thunderstorm severe, but again, flooding kills more people than hail every year across the United States. So flooding's an important hazard, but it doesn't make a thunderstorm severe. A tornado makes a thunderstorm severe. Hail larger than an inch in diameter makes a thunderstorm severe. So that's about the size of a quarter is inch hail. So anything bigger than that is considered severe. And then wind gusts greater than or equal to 58 miles an hour make a thunderstorm severe. And a good rule of thumb is if the wind is strong enough to start knocking down large tree limbs or healthy trees, it's a good rule. It's a good sign that it's more than 58 miles an hour. Usually, if you're not getting any sort of tree damage, your winds probably aren't at severe levels. So in terms of hail, how it forms, so usually every hailstone starts out as a water droplet, and eventually this water droplet gets high enough in the atmosphere that it freezes into what we call an embryo. Once we have an embryo, and around here we actually see these hail embryos make it to the ground fairly often in the spring and fall months. Grapple, so snow pellets, that's basically just embryonic hail. That's the very basic formative hail. Now, normally in summer, grapple doesn't make it to the ground because it just melts way too quickly, but in the spring and fall months, you get days where it's 45, 50 degrees and you get showers, maybe a thunderstorm here and there, and you get, pellets falling out of it. That's usually embryonic hail that just makes it to the ground because it's colder, so it doesn't have an opportunity to melt. So once you get that hail embryo, as we call it, you have super cooled liquid water getting lifted in the updraft of the thunderstorm, and that collects on the hail embryo and allows it to start growing. And assuming the updraft with the thunderstorm is strong enough to suspend this hail aloft, it'll keep growing until it forms a hailstone. So hail tends to grow most readily between the level of the thunderstorm. That is between temperatures of 10 Celsius and 30 Celsius below zero. That is where hail grows most readily in thunderstorms. That's where you have that nice mix of ice crystals and super cold liquid droplets is kind of in that temperature level. So that's between about 16 degrees Fahrenheit and about 10 or 15 degrees below 0 Fahrenheit. That's the level of the thunderstorm where hail grows most readily. So you need this process to last long enough for hailstones to grow to severe levels and then fall down to the ground. So you can kind of see you get the hail embryo, and then you get the super cooled water droplets in the blue. I guess we'll go through that one more time, that sort of collect on it, allow the hailstone to grow. And as long as the hailstone stays in that appropriate temperature level, the updraft is able to suspend it. The hail keeps growing until it falls out. So when we get updrafts with winds blowing up at 150, 180, 200, sometimes miles an hour, that's when we start getting baseball-sized hail or larger. It's very hard to get that around here. Maybe once or twice a year we get a storm that produces hail that big in our forecast area. I guess that's sort of summing up the whole process. So you can sort of make out this hail growth process in pictures of large hail. You see the larger hailstone, and you can kind of see the spikes where the super cold liquid droplets were collecting on that growing hailstone. And hailstones with thunderstorms can get to be huge. That is a 9-inch hailstone there on the bottom. That I can't remember if that's the largest one on record in the continental United States, but it's very close. Pardon me, that's 8 inches in diameter. The largest one on record in our forecast area is softball sized. So that's a little over 4 inches in diameter. And we do have some pictures of hail on some upcoming slides from our forecast area. There they are. So, these are just from the last 2 severe seasons, so nothing from this year yet. So that picture on the left there in Toledo, we didn't have an object to compare that to, but we kind of, measured our own hands here in the office. And depending on how big the hands are, that's somewhere between 3.5 and 4.5 inches in diameter from June 2023 in Toledo. July 2023, that's out in Pennsylvania. That's about baseball-sized hail there. And then the Bloomville, Ohio one, that's actually from last March. That was measured at a little over 3 inches in diameter. So close, a little bit larger than the size of a baseball. So again, if you're ever reporting hail to us, if you can measure it with a ruler, that is the most ideal. If you don't have a ruler, but you can compare it to the size of an object, that's a good substitute as well. And pictures, we always love pictures, just so we can see it with our own eyes, helps us really visualize it. So, I would say hail is our second most common severe weather hazard around here. Straight line winds definitely our most common severe weather hazard here in northern Ohio, northwestern Pennsylvania. You can get straight line winds with all types of thunderstorms, although multi-cell clusters and squall lines are the most common straight line wind producers across our forecast area. Straight line winds result from a combination of storms moving quickly. They literally push the air in front of them forward, along with rain-cooled air crashing to the ground and rushing out of a thunderstorm. So a combination of the storm's movement and how cold the downdraft is determines the straight line wind potential. And this is why very fast moving thunderstorms tend to produce more wind damage than slower moving ones. Usually straight line wind damage, it occurs in one direction, as opposed to tornadic wind damage, which occurs in a bunch of different directions. So one important note for straight line winds, we always try and emphasize this to people. Straight line winds can occur ahead of the rain. They can start rushing out ahead of the rain itself. So straight line winds, they can occur before it starts raining, and it's why people should take shelter before the straight line or before the rain starts at their location. So, how straight line winds kind of start developing and intensifying is once you get a downdraft developing, especially if there's dry air aloft getting drawn into that downdraft is colder than the surrounding air. So it's the exact opposite of instability with an updraft, which causes that air to actually accelerate or rush towards the ground. And once that air reaches the ground, it fans out in all directions and causes wind. So obviously airplanes don't want to fly through thunderstorms because these downdrafts can cause planes to get pushed towards and sometimes into the ground. So airlines know this, they don't fly through thunderstorms. So a particularly focused or specific type of straight line wind is what we call a downburst. And this is what happens when you get a downdraft rushing towards the ground and then hitting it and fanning out in all directions. So you can kind of get an idea of what that looks like there on the right, and we have a couple more animated loops on the next couple of slides that show this better. You see kind of on the leading edge of the rain-cooled air, you can kind of make out just kind of by the shape of the rain that air is rushing out away from the thunderstorm. Downburst winds can, on rare occasions, exceed 100 miles an hour, although much more commonly around here, they're more in the 60 to 70 mile an hour range. A microburst, if you've heard that term before. A microburst is just wind damage that covers an area no more than 2.5 miles wide. A macroburst is basically just a very big microburst. It's the exact same thing. It just covers an area more than 2.5 miles wide. Now, usually macrobursts are more intense and long lasting than microbursts, but it's the same process. So here is a simulation, an idealized computer simulation of a downburst. You can kind of make out the cooler blue colors quickly descending out of the thunderstorm. That air hits the ground and it spreads out in all directions, causing wind damage. So this is kind of an idealized setup, or it's a computer simulation, but on the next slide, if it goes forward, we actually have a real life version of this. I believe this is from Arizona about 3 years ago, but you can kind of see right now, big rain core, big cluster of rain falls out of the thunderstorm, hits the ground, spreads out in all directions. There's another example there. So there were probably 2 or 3 really. Yeah, there's another one right there, downburst within this thunderstorm. So I believe we'll get a more slowed down version here, where you can kind of see, I'll go back just a few seconds so you can kind of see the start of it as it zooms in. You sort of see the light color there. There's probably some hail in that falling out of the thunderstorm, rushing towards the ground, hitting it, and then spreading out in all directions, causing quite a bit of wind as that happens. So yeah, someone made a comment there that they've liked to kind of explain the concept of, you turn downbursts, you turn water on, it comes out of the faucet, rushes towards the ground, and then it hits the bottom of the sink and then spreads out in all directions. That is very similar to what's happening here in a downburst. So, probably uncommon that you'll see something that looks quite like this here in Ohio. Actually, real quickly, let me stop it right here. So this dark cloud here right on the edge of the rain, that is the rain-free base. So probably uncommon that you'll see a whole downburst process like this here in Ohio or Pennsylvania, just because of our trees and hills. But if you can, that's what it looks like. So let's move on to the next slide. Maybe. So here is kind of the type of damage a downburst can do. A downburst can flatten whole areas of trees. Yeah, I'm not sure. Yeah, someone asked, I don't know if anyone else can see the comments there, Marcel. I think it might just be something that we see on our end. Yeah, I don't know if anyone else can see the comments. So yeah, this is the sort of damage a downburst can produce. And here's a more local example from last August 6th in the Chesterland area. One thing that really stands out with both of these is the damage. It mostly occurs in one direction. And you can tell by the arrows that the wind is sort of fanning out as the downburst goes along. So when we see damage like this, with every tree flattened in an area, it does take wind speeds near or over 100 miles an hour to do that. So a very brief break here. If you want to take a couple minutes, I'm going to say at 5:15, I'm going to start talking again. And then we'll try and get this wrapped up by 6 o'clock on schedule. So we'll be back here in a few minutes. I'll try and answer any questions that trickled in while we're gone, and we'll start talking again at 5:15. All right, welcome back. We're gonna finish up the presentation here over the next 45 minutes. Yeah, a lot of questions about the slide deck and recording. We should be able to email out a copy of the slides probably tomorrow, and we will look to upload this recording to YouTube at some point in the near future. So, at the very least, we'll get you a copy of the slides tomorrow. And then we'll try and get a copy of this uploaded because we don't have an advanced version on YouTube right now. So moving on from damaging straight line winds and hail to tornadoes, the third thing that can make a thunderstorm severe. So a tornado is a rapidly rotating column of air. It's in contact both with the ground and the base of a thunderstorm. Or a convective shower, because every once in a while we get tornadoes around here without lightning, usually in the colder season if we do. The good news is only about 1 in 10,000 thunderstorms produce a tornado, so the vast majority do not. And then the tornadoes themselves produce usually a very small and well-defined area of damage compared to the entire thunderstorm. So one key thing to remember, the amount of damage doesn't necessarily indicate whether or not there was a tornado. And the main reason for that is weaker tornadoes can produce, the same amount of damage as stronger straight line winds can. So some terms associated with a tornado, a wall cloud is a lowering, very often rain-free, beneath a thunderstorm. And if that wall cloud is persistent and rotating, that's a good sign that you have a supercell, and that's kind of step one to getting a tornado. So wall clouds, they're impressive looking. They're not causing damage, but if you see a wall cloud, you're pretty confident it's a wall cloud. You can certainly give us a call and report that to us, because that's good information for us to know. That 1 in 10,000 thunderstorms, that is all thunderstorms. That was a question that came in. And then now I'll answer this one now too, just because I think we'll get other questions along those lines. So we don't actually give out spotter IDs anymore. What we do give you is a spotter only phone line to call. So if you have that phone number, we assume you've gone through the training. So you don't need to give us an ID if you call us anymore with a report. Just tell us you're a spotter and where you are and what you saw. So, wall clouds aren't producing tornadoes, but kind of a funnel cloud is the next step. Usually this will develop underneath a wall cloud, and it is, as its name implies, it is a funnel-shaped cloud. It's usually going to be relatively smooth with visible rotation. That is the easiest way to tell if you have a funnel cloud or something potentially tornadic, is if it's rotating, because a funnel cloud like this, you would be able to visibly see the rotation. And then, once you have a funnel cloud, a tornado may not be very far away. A wall cloud is step one, a funnel cloud is step two, and then step three is the tornado itself. And, oftentimes you go from funnel cloud to tornado pretty quickly. And then, here is what a tornado looks like. This is a local picture, so not quite as classic as what you might see out in the plains, but you can kind of see sort of right in the middle there of a wall cloud, and then underneath it, this funnel-shaped cloud comes down and extends all the way to the ground, and that is a tornado. So, in terms of getting tornadoes from supercells, sorry, screen froze on me for a second. There we go. Basically, supercell tornadoes form in what could be called a three-step process. So step one is really just horizontal wind or horizontal spin in the atmosphere that's already there from wind shear is lifted into a thunderstorm, and that gives you a supercell. So that's step one. But you don't have a tornado yet. Step two is, if you recall the supercell graphic, and we'll show it again on one of the next slides just to drive it home. Step two to tornado formation is on the edges of a supercell, temperature differences develop next to the rain-cooled air. And where those temperature differences develop, wind direction differences develop, and that starts causing spin to develop near the ground. And then basically, once you get that spin starting to develop near the ground in a supercell, if the downdraft isn't too cold or too strong to just kind of disrupt the whole process, the spin that develops near the ground will get pulled into the thunderstorm updraft and cause a tornado to develop. So, basically step 1 and 2. So step 1 is basically this big cloud, where it says mid-level mesocyclone developing. And then step 2 is where spin develops closer to the ground, kind of on the edge of the downdraft, and then gets pulled towards the updraft. And then step 3, the tornado developing itself, is when the spinning air that develops near the ground is able to get successfully pulled into the storm. And that was that picture was from Daniel Fouts in Stark County, that Jackson Township tornado. So yeah, and Daniel, I must say, I looked for other tornado pictures in our area since then, and that's the best one we have since 2021. So we don't get photogenic tornadoes very often around here. So, and then step 3 kind of fails. You don't get a tornado if the cold air rushing out of the thunderstorm is just too intense. It causes the process to fail. So, this is back to the supercell schematic. Again, going from a supercell to a tornado is a very delicate process. Basically, you need the air in the rear flank downdraft and the forward flank downdraft to not be so cold that it completely cuts off that yellow inflow. If it does, you don't get a tornado. But if that yellow inflow is able to sort of stay in place, that's when you can get a tornado. So it's a very delicate process, and that is why we sometimes issue tornado warnings based off of radar indicated rotation that don't produce, just because the process is delicate and it can be disrupted quite easily. So a couple pictures of maybe tornadoes, maybe not. These are from Pennsylvania in October of 2018. I'll give you a second to decide if you think these look like tornadoes or not. And so the one on the left from Tish Evans in Cumberland County, Pennsylvania, that is not quite a tornado. That is a wall cloud in the middle with a nice rain-free base and maybe a little funnel cloud, but that funnel cloud is not extending anywhere near to the ground on the left. And I saw a couple of people commented it looks like a wall cloud on the left, and I would agree. It's a wall cloud, maybe a funnel cloud, but probably not a tornado because it's not in contact with the ground. And then on the right, that is also not a tornado. That is just a tail cloud getting pulled into a thunderstorm's updraft. And the reason, or the way you would be able to tell the one on the right is not a tornado, is because you would not see rotation if you saw this out in real life. So it's kind of a scary low-hanging cloud, but it would not be rotating, and that would mean it's not a tornado. Now, both of these two, on the other hand, I'll give you a second to sort of process them. These are both tornadoes. So the one from May 2019, that's from Pennsylvania, you can kind of make out that cloud extends all the way to the ground. You would be able to see rotation in that cloud. It's right on the edge of the rain shaft. You can kind of see the rain shaft to the left of the tornado, the rain-free base just a little to the right of the tornado. So very classic tornado. So the one on the right is also a tornado. Now this one's a little bit trickier because this is from our local area. And yeah, I see a couple people commented this. The cloud is not on the ground, but you can see debris lifted in the air. So in this case, it definitely was a tornado. This was actually a fairly strong tornado. It was an EF2 tornado in Huron County, Ohio. a couple of Junes ago. So yeah, the giveaway here is you can kind of see from the rain whipping across the ground and over the roofs of the building that the rain, the air is kind of getting sucked into this tornado. You can also kind of see that the tree on the left is getting pulled in towards the tornado, and you can see a pretty large piece of debris in the air there, sort of in the upper middle, just to the left of the funnel. So, you know, if you see a funnel cloud not extending all the way to the ground, but you can see like debris getting kicked up underneath it, that is a tornado. So here's what a tornado looks like on Doppler radar, and this was from an EF2 tornado last March. So, you know, one important thing to keep in mind is because of how small tornadoes are and how radar beams work, they get higher off the ground the further away from the radar that you get. And on top of that, the radar beam gets a little bit wider the farther away from the radar you get. Because of all that, unless we are looking usually within 10 miles of the radar, if it's any more than 10 miles away from the radar, we are not seeing a tornado. We are just seeing the mid-level rotation in a supercell. So, you know, usually the stronger the mid-level rotation is, the more likely it is to produce a tornado. But when we are seeing radar indicated rotation, we're not seeing a tornado. So that is why spotter reports really help us out. And this is base velocity on the right. So yeah, the two radar things you're looking at, I'll you know, help you get your bearings. On the left, that is just what we call base reflectivity. It's showing precipitation getting picked up by the radar beam. You know, you turn on the news, they show the radar. It usually is reflectivity, which is what you have on the left. On the right, that's what we call velocity. This is base velocity in this case. So it is just showing the winds blowing towards or away from the radar located at Cleveland Hopkins Airport. Now, since we are not seeing a tornado itself on radar unless it's very close to the radar, that is why spotter reports telling us, yes, there's a tornado, or no, there's not a tornado, really helps us improve our tornado warning decisions, and also helps us increase the urgency because we are in constant contact behind the scenes during these severe weather events with, you know, say members of the media, local emergency managers, and we can kind of tell them behind the scenes, like, hey, we are getting spotter reports. There is a tornado here doing damage, and they can kind of increase their urgency on their end. So just because we're usually not looking at a tornado on radar, we're looking at rotational off, spotter reports, very important to us. So how does tornado damage differ from straight line wind damage? The way it differs is straight line winds, usually the damage is all in one direction and it's sort of fanning out from the middle. Tornadoes are the opposite, whereas it's in different directions and everything is sort of blowing in towards the middle of the damage path. So when we're out doing damage surveys, a lot of times, you know, that is how we make the determination, weak tornado versus straight line winds, is the direction stuff was blown down in. So now here's a couple other examples of tornado damage. You know, when tornadoes hit cornfields, it's not good for the corn, not good for the farmers, but it can give us some very helpful damage patterns because we can literally see the swirls in the damage pattern when crops, and usually around here corn, are hit by tornadoes. So here is a local example. This is from April of 2019. This was an EF2 tornado. It touched down near Shelby, Ohio in Richland County, the county Mansfield is in. And you can sort of see how all the damage kind of converges towards the middle of the path, indicating it's more tornadic than straight line wind. Another picture from that same event, you can kind of see how all the debris from all the buildings that were damaged was sort of funneled towards the middle of the tornado path. So, you know, that's a telltale sign for us that it's a tornado as opposed to straight line winds. And then, you know, just a few pictures from around here of sort of how bad tornado damage can get in northern Ohio, northwestern Pennsylvania. Most of our tornadoes are fairly brief and weak, but every once in a while we can get some violent ones. And yeah, someone asked about, aerial photography for tornadoes. Yeah, if we can ever get, either from a drone or a helicopter footage of a tornado damage, it does help us make that determination. So this is from June of 2010, Millbury, Ohio, that's in Wood County, just south of Toledo. And this was the last EF4 tornado in our forecast area. Completely destroyed some houses, unfortunately resulted in several fatalities. So we can get some very nasty tornadoes around here. Fortunately, they're not extremely common. Going back a little further in time, this was from November of 2002. We had an F3 tornado, a very high-end F3 tornado hit Tiffin, Ohio, and it more or less destroyed a couple of houses right there. And then a very strong F2 tornado hit Macedonia, Ohio. And fun fact, I was much younger at the time, living in Solon, Ohio, which is just a couple of cities over from Macedonia. And that same tornado went through my neighborhood. So certainly an event that might have helped lead me to where I am today as a meteorologist. And then some more recent tornado damage pictures. These are all from EF2 tornadoes in the last couple of years. The pictures from Toledo and Oak Harbor are from the same day, different tornadoes, both EF2s that, they didn't totally destroy those buildings, but they rendered them, completely uninhabitable and essentially destroyed them. And then the picture in the middle is from last March in EF2 Township in Plymouth, Ohio, which is right along the Crawford-Richland County border. What you're looking at is what's left of a mobile home where those cinder blocks are. And mobile homes, trailers, very dangerous in tornadoes because the mobile home was completely lofted and thrown into those trees. Even with an EF2 tornado, it completely, if someone was in this mobile home, they'd be very seriously injured or perhaps worse than that. So yeah, mobile home's not a good safe spot to be in tornadoes. So kind of talking a little bit more behind the scenes stuff here, we look at a number of computer models to try and assess the atmospheric conditions in place. So that's where you get into the SLIM, the acronym, the shear, lift, instability, moisture. We look at both current observations if it's the day of, and then usually if it's further out in time, we look at computer models to get an idea of how supportive the atmosphere is for severe weather. And then on top of that, some of our computer models can actually attempt to simulate the development of thunderstorms. And we can sort of take a combination of the expected atmospheric conditions and when and where storms may develop, and sort of combine that into an idea of when and where severe weather may occur. Severe weather or forecast models have quite a bit of error sort of built into them. I would say the most common thing that sort of trips up the models around here is if we have rain or thunderstorms in the first half of the day. Sometimes the models struggle to resolve how warm and humid it will or won't get later in the day, which significantly influences instability. But there's quite a number of tools we look at when trying to forecast severe weather. Some forecast computer models are, cover the whole planet. Others only cover maybe the entire lower 48 or maybe even a smaller part of the lower 48. The higher the resolution of the model, the better the shot it has of maybe simulating a thunderstorm, but computer power is sort of limited. So those very high resolution models, they usually only run, 1 to 2 days in the future, and usually they don't cover the whole planet. So, models run at different times. They spit out forecasts. Some of them spit it out every 15 minutes. Some do it every hour. Some do it every 6 hours. Models cover different sized areas. So basically, it's sort of a game. Depending on what we're looking at, we'll look at the models that sort of suit the situation the best. So if this, if we're looking at potential severe weather 5 days from now, we're probably looking at models that run out further into the future, cover the whole planet, and we're maybe looking at those for a general idea, whereas if we're drilling into it the day of, we might look at a much more focused computer model like this that can actually show individual storms developing. So we're going to kind of put all of this together with 2 case studies. One of them is going to be fairly in depth, this first one, and then one of them will be a little quicker, covering an event from last summer. So we're going to try and sort of tie together all the thunderstorm ingredients and that were in place on these days and put it together into how it all played out. So the first event was from May of 2022. This was an event that produced a nice smattering of damaging winds and large hail across our forecast area, no tornadoes. This was, I'd say, a very common sort of setup around here for the spring and summer months. So we're starting off with a look at the jet stream this day. And you can sort of see where there's all this color fill. There's a very strong jet stream just a little bit off to our west and northwest. We're sort of on the fringes of it. But as that jet stream is moving in, it is providing some amount of wind shear in the atmosphere, enough that we're going to get more than pulse thunderstorms. So moving towards, this is about 5,000 feet aloft in the atmosphere. The blue and red contours are temperature. The green contours are dew point at that level. And they're kind of hard to see, but the barbs are wind speed and direction a few thousand feet aloft. So a couple things you can sort of make out. You can sort of see those deeper greens building over Ohio and Pennsylvania, indicating that we had good moisture in place. And you can also make out a very sharp gradient just to our northwest, sort of from northwest Ohio across Lake Erie into southern Ontario, where the temperature and dew point lines are packed real close together. And there's even a bit of a wind shift across that. So there's a cold front coming in. So what we have is a cold front coming in, adding some lift, and we do have some good moisture in place ahead of that cold front. So with that moisture in place, it was a very warm, humid day. The sun was out ahead of the cold front, and that led to plenty of CAPE. If you think back to the instability or CAPE table, once you get more than about 2,000 joules per kilogram of CAPE, we consider it to be a pretty good amount, certainly enough for severe weather. And this day we had 2,000 to 3,000 plus joules per kilogram in place ahead of that cold front that was coming in. One thing to note, it was May, so Lake Erie was much colder than the land around it was. That's very common in the spring and early summer. The lake takes a long time to heat up. So instability is much more limited over Lake Erie, and you can see that blue shading. That's what we call convective inhibition, or CIN, C-I-N-H, over Lake Erie. And what convective inhibition is that's telling us that even though there's some instability, that there's a level somewhere where the instability is not there. So something's going to need to force the thunderstorms through a stable layer, and in this case, it didn't really happen over Lake Erie. Moving on from sort of instability to wind shear, this is just 0 to 6 kilometer wind shear is a very common level of wind shear that we look at. And on this day, there was about 30 to 40 knots of wind shear across most of our forecast area, increasing once you got over Lake Erie and into Michigan. So 2,000 to 3,000 joules per kilogram of CAPE, 30 to 40 knots of shear. So we have plenty of CAPE, and we have enough shear for some organized storms, but it's kind of right on the fence for supercells. And then here's a look at the surface map and satellite from that day. So you can see, this front extending from, near St. Louis through Indiana, Illinois, into extreme northwest Ohio and southeast Michigan, and that was pushing southeast into the area. And you can sort of see on satellite that not too many clouds here over northern Ohio or northwestern Pennsylvania ahead of the front or ahead of the lake breeze. You can see that little dashed line near Lake Erie, that's a lake breeze, which can act as a source of lift for thunderstorms. So here's a much more zoomed in surface map with some hand-drawn fronts. Cold front pushing into northwest Ohio, very warm and humid in front of it, temperatures generally in the mid 80s, with dew points in the mid to upper 60s. And then these two dashed lines, the light pink dashed line, that is a lake breeze, and then the darker purple dashed line here towards central Ohio, that is a prefrontal trough. So when you sort of put it all together, before we delve into what happened, we had plenty of sources of lift this day. We had a cold front, a lake breeze, a prefrontal trough, and for good measure, we had storms kind of moving up into our relatively higher elevations away from Lake Erie. We did have an approaching upper level trough, which adds a little bit of lift and also adds some wind shear, a moderate amount of wind shear, 30 to 40 knots. We had plenty of instability present, 2,000 to 3,000 joules per kilogram. So a lot of ingredients seem to be in place for severe weather. And we'll examine a few more specialized parameters, just a bit more, and kind of show you what happened. So if you think way back early in the presentation when I talked about an elevated mixed layer, one way for us to measure that is by measuring the lapse rate. Remember, that's how quickly the temperature cools as you go up through the atmosphere. We can measure the lapse rates in the mid-levels of the atmosphere where an elevated mixed layer would be. And on this day, we had mid-level lapse rates that were a little bit steeper, 7 to 7.5 degrees per kilometer, which is indicative of some form of an elevated mixed layer or EML in place. Elevated mixed layers, when we get them, tend to correspond to our largest hail. So if you think back to that hail picture from last March, actually, where we had 3-inch hail near Tiffin, Ohio, in Bloomfield, we had an elevated mixed layer in place that day. So this is a different parameter that we haven't talked about at all yet. This is called D-CAPE or downdraft CAPE. This is pretty much the opposite of CAPE. So CAPE itself measures how robust or how strong an updraft in a thunderstorm can get. D-CAPE measures how strong a downdraft in a thunderstorm can get. And if you remember, a lot of straight line winds develop just from cold air rushing out of, or downdrafts, pardon me, kind of developing and then rushing out of a thunderstorm. So more downdraft CAPE increases potential for wind damage. And then this is just a look at the same, this is low level lapse rates closer to the ground. This helps show us where thunderstorm winds are more likely to make it all the way down to the ground. When lapse rates near the ground get weaker, it is a little bit harder to get strong downbursts. But on this day, we had very steep low-level lapse rates, as we call it, which makes it easier for strong thunderstorm winds that develop aloft to rush all the way down to the ground and produce wind damage. So, just based on the steep lapse rates, both aloft and near the surface, it is a pretty good environment, along with the downdraft CAPE for damaging winds and large hail this day. If you remember back to storm relative helicity, that takes into account the amount of wind speed increase through the atmosphere and also how much turning there is in the atmosphere. And helicity, the higher it is, the more conducive it is to tornadoes. On this day, we had pretty low values of storm relative helicity, so maybe arguing against a tornado. So, sort of putting it all together, thermodynamically, and by that I mean the amount of instability or CAPE, the low to mid-level lapse rates, and the downdraft CAPE all supported a risk for severe weather, including damaging winds and large hail. There was enough shear for storms to be organized, but it was a little bit on the lower end for supercells and tornadoes. Plenty of lift, and some upper level lift and forcing as well. So what was the result? We had an initial batch of thunderstorms kind of pass just to our north in the morning that day, and then we had thunderstorms develop basically all over the place on those various sources of lift in the afternoon. And it was those afternoon storms that ended up being the most severe. So the morning storms miss us. We stay sunny and warm until the early to mid-afternoon, and then by 2, 3, 4 o'clock, we have storms developing all over. They developed along the cold front, the prefrontal trough, and the lake breeze. And here were the resultant damage reports. A lot of wind damage and several reports of larger hail, including a couple reports of hail larger than 2 inches in diameter east of Cleveland. So I'm going to take a closer look at a couple of pieces of this on radar. One is just kind of a look at the evolution across northwest and north central Ohio, where most of the wind damage occurred. And most of this wind damage sort of happened kind of from the upper Sandusky area up towards Tiffin, over towards Norwalk, Willard, Bucyrus, Shelby, north of Mansfield. And most of this damage happened when we had this little line of storms sort of organized, and you can see it's surging forward, almost takes on a little bow echo in there. That's reflectivity on the left, base velocity on the right. And you can sort of see on the right how there is a little push of stronger winds aloft within that line of thunderstorms with those brighter blues indicating winds blowing towards the radar near Cleveland. And then that 2-inch hail in Geauga County east of Cleveland actually came from what was a very small supercell. This supercell did not produce a tornado. Yeah, someone asked a great question. What happens when the storm moves into the next NWS region? So it is a very sharp cutoff, but we talk to our neighboring weather service offices, and if we issue a warning along our border or vice versa, we let each other know so we can make sure the warnings are seamless if we can along those borders. So this was a supercell, and a couple things I outlined here. You have reflectivity in the upper left, and you can see a little hook echo there in the circle, and you can also see a yellow dashed line. That is the storm's gust front rushing out ahead of the thunderstorm. So right there, we already know it's probably not going to produce a tornado because you have that strong, cold downdraft rushing out ahead of the thunderstorm, disrupting that potential tornado process. On the right, we have storm relative velocity, which basically is just showing you don't really see any rotation there. You don't see reds next to greens, which is what we look for rotation. Bottom left, VIL stands for vertically integrated liquid. That just tells us how much liquid the thunderstorm has lofted, which just gives us an idea of how strong the updraft is. And bottom right, echo tops. That's telling us how tall the thunderstorm is. In this case, it was almost 50,000 feet tall. So what this slide shows is just sort of a vertical look at the thunderstorm. So once you get up, 7 to 10,000 feet, you do have some rotation in there, some red next to green, but not closer to the ground. And that's what prevented any sort of tornado from developing. Also note, 24,000, 30,000 feet on the left, we still have, and this will go back through, some very high reflectivity indicative of very large hail through a deep layer of the thunderstorm on the left. So this thunderstorm, it was a supercell. It did not produce a tornado, just not quite the right atmospheric combination for a tornado, but it did produce hail larger than 2 inches in diameter, which is always pretty noteworthy when we get it up here in northeastern Ohio. And here is a vertical look at that reflectivity showing that very strong supercell updraft, creating a very tall hail core through a deep level of the thunderstorm. So you can sort of see the heights, let me go back, on both the left and right side. And you can see the radar's picking up large hail well over 30,000 feet aloft, which is certainly something we look for larger than golf ball sized hail. And we did see larger than golf ball sized hail with the storm. And then one more little cross section here. This is with that same cluster of thunderstorms that produced the wind damage out in north central and northwestern Ohio. And what I want you to note is how early in the loop you get a really tall thunderstorm moving left to right across the middle here. But that quickly sort of collapses. And as that thunderstorm collapsed, that's when the bulk of the wind damage occurred, because you had a series of downbursts that occurred as that kind of entire cluster of thunderstorms sort of collapsed. And this is sort of a classic multi-cell cluster. You see new thunderstorms sort of continually developing on the leading edge, and then sort of getting overtaken by the rain-cooled air. So that was the more detailed case study. I did want to quickly throw in a few slides touching on that August 6th event from last summer, just because, again, in the Cleveland area, one of the most significant events we've had in the last few decades, quite frankly, in terms of number of power outages. So starting off with the winds, many thousand feet aloft. This is about 35,000 feet aloft. You can see a belt of stronger winds in the blues, sort of just grazing northern Ohio with much weaker winds aloft further to the south. And one thing that is pretty pronounced, this was the morning before it happened, so a few hours ahead of the severe weather, you can notice a very well-defined sort of kink in the winds moving into the western Great Lakes. That's what we called a shortwave trough, which is a source of lift moving into the west. So whenever we have a lift sort of moving in from the west during the afternoon in the summer, that's something that sort of gets our antennas raised for severe weather potential. Here's a quick look at the fronts that day. We had a warm front draped across northern Ohio with a little wave of low pressure tracking along it. And if you remember much earlier when I said, how do you get a lot of low-level wind shear, that's favorable for tornadoes, and I mentioned stronger low pressures and warm fronts. This day had a warm front and a weaker low pressure, but it was certainly enough between the two. Instability this day, it was not crazy, but was certainly sufficient, between 1,500 and 2,000 plus joules per kilogram, with a very sharp gradient as you moved towards the southern Lake Erie shoreline. There was no instability up north because you were on the north side of the warm front. The mid-level lapse rates this day were much weaker than the last example. So the last example, these mid-level lapse rates were 7 to 7.5 degrees Celsius per kilometer. We had hail larger than 2 inches. This day, the mid-level lapse rates were weaker, and we did not really have much hail this day. And the downdraft cape this day, interestingly enough, there was some, but it wasn't crazy. It was really between about 600 and 800. So what this tells me is that it was really just the dynamics of the thunderstorms that produced a lot of the wind damage this day, as opposed to something like a pulse thunderstorm. Then this is a look at the low-level moisture this day. We will give you a spotter phone number towards the end of the presentation. I see a couple people asking about that. We will give you our spotter phone number here in just a few slides. So what this plot shows is this is just showing where low-level moisture is greater. And once you're getting into the yellows, that's sort of maxing out the scale here. If you remember back to this day, it was a very humid day. Dew points were in the low to mid 70s. So that very intense low-level moisture helped develop a good amount of instability just south of that warm front across most of northern Ohio. So lapse rates aloft were pretty weak this day, but the lower level lapse rates were much stronger. So the strong low-level lapse rates, it was very warm and humid. Temperatures were in the mid 80s. Dew points were in the low to mid 70s. Even without, those good mid-level lapse rates, just how warm and humid it was closer to the ground was enough to give us that 2,000 joules per kilogram of CAPE this day in August. So what we did have this day was a pretty good amount of shear, 40 to 50 knots across Lake Erie and far northern Ohio, with less shear as you headed further south. And you'll be able to see what that did to the storms on radar here in a couple of slides. So this plot really sort of combines everything into one. And so this is something we sort of like looking at here. So the red contours, that's just your cape. The blue wind barbs, those are shear in the lowest 10,000 feet, which is especially important to squall lines. And we had a squall line this day. And then the color fill, that represents something very similar to D-cape. So just a nice little area there across southern Lake Erie and far northern Ohio, where the instability, the shear, and then the stronger downdrafts really aligned nicely, and that's where the bulk of the severe weather occurred. So here is how that played out on radar. So there was no severe weather over Michigan. This all developed over northwestern Ohio and Lake Erie, and then just quickly blasted across most of northern Ohio and into western Pennsylvania. And then this was the example I showed earlier in the presentation of a very intense squall line that wasn't technically a derecho just because it didn't last long enough, but it was a very intense squall line overall. So a couple things I'm going to point out. One is how organized the storms were across Lake Erie and northern Ohio. They're organized into a line with very strong velocities feeding into it. You can see on the right. Whereas everything further south was much less organized, and that was due to the lack of wind shear farther south. So, you know, the proximity to the warm front and just the stronger wind shear really helped organize these storms up in the Cleveland area and over Lake Erie. So this was a squall line that produced very strong straight line winds and 5 tornadoes in the Cleveland area. And you can sort of see as the storms push into the Cleveland area, some very brief areas of rotation that are evident on the right-hand side of the image, where you get, you know, those reds and greens right next to each other. That's what we call a velocity couplet. You can see a couple of them briefly. That's very common for squall line tornadoes. You just get small, brief areas of rotation on radar that don't last long, whereas usually with supercells, we get longer lasting areas of rotation on radar. Here's again, one last look at the damage reports. We estimated up to 100-mile-an-hour straight line winds with this, along with 5 tornadoes. We had no large hail reports this day. And I think that's the function of A, the storms were organized into a squall line, as opposed to something like a supercell. And B, we didn't have those really strong mid-level lapse rates like we would have with an elevated mixed layer. That tends to help support larger hail. So I think between those two things, we had a lot of wind, handful of tornadoes, but no large hail this day. And you can note the damage really was focused in a narrow corridor where that sort of bow echo went here across the Cleveland metro in northeastern Ohio. And then we had some wind damage here and there with those less organized storms further to the south and southwest. But as I go back to the damage reports, much more intermittent damage outside of that bow echo. And again, power outages lasted up to about a week in the Cleveland metro area. So where to get our forecast information? Our website, weather.gov/CLE, takes you to our homepage. You know, if you want to look at the Storm Prediction Center, they issue convective or thunderstorm outlooks up to 8 days in advance, and they really dial it in 1 or 2 days in advance. You know, they'll break it down by the risk of tornadoes, hail, straight line winds. That website's there, sbc.noaa.gov. The Weather Prediction Center, they analyze where fronts are. They also issue outlooks for things like flash flooding. That is what their website there, wpc.ncep.noaa.gov. And then, so yeah, I had a few questions about this. So if you want to register to become a spotter, if you just want to scan the QR code or copy and paste that link there, I believe I can put this in the chat. Maybe I don't know if I can copy and paste it in there. But you can, you know, if you just scan the QR code, give us your information, it'll log you in our system as a spotter. Now, so I believe it's the next slide that has how to report. And I've gotten a handful of questions here in the last couple of minutes about how to report. So I'll get through that last slide and we'll see if there's any remaining questions. So if you are reporting severe weather to us, so severe weather, that's, wind damage, hail, a tornado or something like a funnel cloud or wall cloud. What we need to know is when it occurred. So basically, is it happening now? Did it happen in the past? Where you are, as close as you can get, the condition, what you're seeing, and who you are. And yeah, if you have registered for us in the past, I have someone asking, if you're already a trained spotter, you should already be in our system, especially if you've done it in the last, let's say, 5 years. But if you aren't sure, you can send us an email and ask. So again, real quick, here is a good idea of what to report. And I didn't mention flooding on that last slide, but certainly, if you see an unusual amount of flooding that can be hazardous to people, maybe it's threatening homes or businesses, or could, sweep vehicles away, that is certainly something we appreciate reports of as well. So here is the information how to report. So I would say, in terms of getting reports to us quickly, the unlisted phone number is probably the best option, because if you call that unlisted spotter number, it rings directly through to our operations area 24/7. A forecaster will always answer the phone and take your report, and then we have it right away. I would say stormcle@noaa.gov, that is our spotter email address. So if you ever maybe want to give us a picture or a video or something you want us to take a closer look at, that's a good email. The only hang up with StormCle is in the heat of the moment, we are not checking our email. We'll get the reports after, but if there's something you want us to know right now, the phone call is the best way. You can also submit reports to us on social media. I would say Twitter, or formerly Twitter, now X, is probably the most immediate way for us to get it, just because we can very easily sort, people who are tweeting at us. We can sort that quite easily and view those quite easily. But Facebook is a good spot as well. So I would say social media or the phone call, most immediate. StormCle, the email, that's best for reports after the fact. Along with all these sources, we do also work very closely with a handful of ham radio operators who take reports from other ham radio operators and relay them to our office. In bigger severe weather events, we'll actually call these ham radio operators into our office to relay reports to us. So I guess, got some questions on certification. So if you scan this QR code and put in the code right there, it is 2025 Skywarn. As long as you registered for the class, you should be able to get a personalized certificate. So I see a couple of questions that came in. I totally get it if you don't want to put stuff on social media, what you saw, where you were, your location, stuff like that. Totally understand that. So always feel free to just give us a phone call if you don't want to, post on social media. And again, the email is also a good option if you don't want your report out there, where anyone can see it. And then a couple other questions that have come in. In terms of whether or not we're joining any other social media outlets, unfortunately, that's above our pay grade here at the local office. I do know that there are folks, higher ups in the Weather Service, they're always, sort of looking at the latest social media platforms and looking at which ones may be best for us to join. So, hopefully stay tuned on that one. But for now, we're just on the ones I mentioned: Facebook, Twitter, X, and Instagram. And then, in terms of, if you're interested, if you're a radio operator and working with us during severe weather, just send an email to StormClee, and we can get you more information on that. I'm just answering some questions that trickled in. So there were 2 QR codes. I'll leave this one up for about a minute, just in case someone needs to grab it. I saw a couple numbers. So if you want to, join our spotter network, if you're not already a spotter, not already registered with us, scan this QR code, and then I'll, after about 30 seconds, I'll go back to the next QR code. Unfortunately, we don't have a number to text for reports. Let's see, I saw a question about that. So unfortunately, the only ways we have to report directly are the phone call, the email, or on social media. Unfortunately, right now, we don't have a way to text us reports in a way that we would get it immediately. So I'm going to go back to to this slide one more time real quickly with our phone number, email, and social media handles. And we'll finish up on this slide if you'd like your certificate. So that is all I have today. I'm going to hang out around for maybe like 3 to 5 more minutes. We'll say until about 6:10 if any questions trickle into the chat. Otherwise, we will look into emailing these slides or a video recording of the presentation out to those who registered. Otherwise, we appreciate all of you joining us, taking the interest in the advanced Skywarn program. At the end of the day, any reports we get in severe weather situations are so valuable, and we really do appreciate. I am just now seeing that I'm not on the Skywarn certificate slide. So if you want your certificate, there you have it.